In this final segment of the EEG analysis tutorial, I'd like to cover a few things that are not essential for the pipeline, but nevertheless they are important aspects of EEG analysis and things which you might be interested in learning. The first of which is how to actually get the p-values that we've calculated from doing our t-tests. So let me show you that very quickly. The file that we computed is here in Brainstorm. It has a file number of 1351. To actually get the p-values, I need to go into MATLAB. To do that, I'm going to right-click on the file, and I'm going to tell Brainstorm I want to go to this directory in MATLAB. So it should bring up that directory inside the MATLAB software. I'm going to double check again. The file number is 1351. I'm going to go and I'm going to open MATLAB, and it has the directory open, and here's my file 1351. I'm going to double click on that and we'll open the file contents in my workspace over here. What I'm looking for is a matrix called PMAP. It's currently a three-dimensional matrix because we have three frequency bands inside of it. The frequency bands are in order: theta, alpha, and beta, and they exist on this third level here. In order to extract those, I'm going to give you one technique to get theta, which you can apply then to the other frequency bands if you want those p-values. A very simple equation. I'm going to say theta p-values are equal to PMAP, and I want all of my channels, and we'll take all of that level, which is my time dimension, and I want the first layer. And since I don't want to print out the values, I'll add a semicolon at the end and press enter. And now MATLAB has added a new matrix called theta p-values. This is a regular flat matrix, and we can double click on this and it will open the values here. Now you can see, because this was fabricated data, all of these p-values are the same at all channels. That's all right. If you're working with real data, of course, that's not going to be the case. But the idea is that now they're in a state which you can copy and paste, you can put into a spreadsheet, you can share with your statistician, or you can report in your manuscript. A final caveat here: the number of the row represents the number of the channel in your EEG recording. So if you know that here you had significant differences at FC2 or FC6, well, you need to know what channel number those are. In order to find that out, we need to find the row names. That exists here within this file contents. You can double click on row names, and now we can see the corresponding names according to the row number. So this can also be copy pasted and placed into an Excel file. Obviously you need to transpose the data so that it aligns with your p-values, but then you'll have the most important elements for reporting your p-values and your results. A couple more things that may be of interest for those performing this analysis in Brainstorm. Some other visualization techniques for the data. For example, when we looked at the mean normalized activity, we only looked at the topographical map, but we can also look at the power spectrum of the data. And by doing so, we can see lines which represent every channel in the data, and then we can see the amplitude of those channels at the three frequency bands that we extracted. So we have the beta here, the alpha here, and the theta over here. So you can see that in general for this high cognitive load file, the alpha amplitude or the normalized power of alpha is very low. Theta tends to be more in positive values, and beta also is negative values. So it's a good way to compare the three different frequencies and their interrelationship. And finally, one more view that I didn't show you, which is possible. Before we averaged over time, it is possible to look at all the channels not as a topographical map, but as an image of channels by time, like this. So you can see we have time down here in the x-axis. We have all of our channels here like this. And now you can see how the envelope activity of the Hilbert transform extracted amplitude is changing over time, and we can shuffle between our two frequency bands. This can be useful to identify problematic channels, or in cases where we have specific event onsets that you might be interested in targeting, where the timing was not perfect enough to use an ERP-based approach, and you use an envelope extraction like a Hilbert transform here. We can still identify those events of interest using a visualization approach like this. So when you go to write your paper, one of the things you'll need to do is write a method section. And in that method section, you will be expected to describe the exact processing steps which were applied to your raw data. So for the most part, I think that's understood from watching this video. But what I mean by that is you don't need to explain that you imported a file into the system. You need to be able to explain things like you visually inspected the data and you checked for dead channels and you removed them if they were present. You performed an independent component analysis and you removed what? You removed artifacts related to physiological noise, such as blinks or saccades. And then you need to describe that you epoched the data. So what was your epoching method? To what extent did you divide the data? And where did you start that process? In our case, we started that process at the onset of certain tasks, which were important in our experiment. Low cognitive load task, high cognitive load task, our baseline. You need to mention these things and say that this epoching process happens specifically in line with the timing of those event onsets. And then you need to say the length of your epochs. It's important. And finally, you need to say what sort of frequency band extraction method you used. We used Hilbert transform. Okay, what frequencies? Theta, alpha, beta. What were the exact parameters of those bandpass filters used there? It was 5 to 7 for theta, for example, 8 to 13 for alpha, etc. You need to provide those details so that somebody, if they received your data, could go back and duplicate the results that you're reporting. And finally, you need to describe how you did the visual inspection of the epochs, that you removed ones with residual noise, you averaged across the epochs, that you did the normalization procedure. What kind of normalization did you use? What was the formula that represented your normalization? I pointed that out when we looked at normalization. There's a formula in Brainstorm. You can actually report that exact formula in your paper. You need to report that you averaged over time. What time window did you average over? So we epoch the data, we had that overlap at the end. So you need to say that you excluded that. You averaged over a time period that excluded that, the edges of your epoch, which had your filtration artifacts inside them. And then finally, you need to report on the statistical test used. So we used a paired t-test, so you report that, and then you need to report any correction factors that were applied, and of course your alpha level. Another important thing that might be required when reporting your data in an official academic manuscript is that you need to report the descriptive statistics, not just the p-values, but the actual values of the amplitudes for your different frequency bands and the standard deviations. In order to access that, we need to go back to the original files that we used in the statistical test and brainstorm. So that means the individual participant files for the two tasks of interest, the high and the low cognitive load. There are a few approaches that work for extracting that in Brainstorm/MATLAB. I'll show you one very quickly right now. You can extrapolate from this how to scale this technique for more participants and other tasks. So very quickly, I'll go back to my time averaged, normalized Hilbert map for my high cognitive load task. I'd like you to imagine that I have multiple participants, and I'm going to pull that file in for that task from 5 different participants. So just imagine these are 5 files from the high cognitive load task. They have been time averaged and normalized, 5 different participants, and I've loaded them in here. In order to simplify my life in extracting the values, I'm going to concatenate these files into one file. And I'm going to do that along the dimension of time, or the x-axis. So in other words, I'll have all my channels lined up on the y-axis, and I'll have my participants in columns along the x-axis. To do that, I'll go to Run. I'll go to the pipeline editor here. I will go to Standardize, and I'm going to concatenate in the dimension of time, or along the x-axis. Click on that, say Run, and now we've made a concatenated file. You can see concat is written here. And this file now contains all 5 of these participants' data. And I want to go and now extract the values that are contained within. So similar to what I did for p-values, I'll right-click on this file. I will go to this directory in MATLAB. And I'm going to now be looking for a file with the name concat inside of it. Here we're inside the directory for the high cognitive load task for subject number 1, where we just were. And there are a number of Hilbert files. I'm looking for this one right here that says concatenate. I still have my t-test file open in my workspace, so the first thing I'm going to do is clear that out of the way. Clear. My workspace is clean, and I'm going to open up this concatenated file. All right. And now what we want are the values that are inside a matrix called TF, which is short for time frequency. You can see that the first part of the matrix is 32 layers. These are our channels. Then it's 10. This is our time layer. We had 5 participants. In every brainstorm file, time always has 2 values, a beginning and an ending value. Even though we averaged over time, Brainstorm always structures its files that way. So if we have 5 participants, it should be 5 times 2 time values, which is 10. And then we have our frequencies here in the last part of the 3-dimensional matrix. I'm going to show you how to extract theta. Again, that's the first level of the 3rd layer of our matrix. So I'll say theta values equals TF. Use colon, comma, colon. So we get all the data, and we'll only take the first layer of the frequency band portion. Add a semicolon to prevent printing. And now MATLAB has made that matrix for us. I can double click on that. And of course, I used the same participants' data to simulate this process. In reality, each participant would be 2 columns like this, and the values would be different. So you would see different values in these column pairs as you went forward. The idea is that you can, similar to the p-values, you would select all of these, copy, paste them into Excel, and then add to that your row names, which you can get here, transposing that obviously. And then the final thing you would need to do is to identify the columns according to the participants. Now here it's a little tricky. You need to make sure that when you load those files into the processing window in Brainstorm here, that you're very careful about the order you put them in there, because the order you put the files in here is the order in which they're going to appear in the column rows. So you need to take careful note of that. You can always go back and double check, but it's good to have notes being taken the whole way through, so you can always go back and see what you did. And as you can see, the interface is not the greatest. You can't really identify the participants so easily here, so taking notes is always a good idea. Good luck.